Okay, let's look at a past exam question based on the mechanical properties of materials. So this question was worth 35 points, and I think it's pretty straightforward as long as you track your work. So the solid tube is 900 millimeters in length and has a diameter of 25 millimeters before being subjected to an axial force of 40 kilonewtons. If Poisson's ratio is 0.344, find the new length and diameter of the tube after the loading. So they also give us a graph of stress versus strain. Alright, so here I kind of started out by writing down all the things we know. We know initial length, initial diameter, Poisson's ratio, the force, and we're looking for the final length and the final diameter. And also all of the equations that we know are along right here. So strain longitude, strain latitude, Poisson's ratio, and normal stress. So the first thing I started with is using the graph to determine the elastic modulus E by using this 450 divided by 0.00225, and that gives me E equals 200 gigapascals. So that's the first step. After I found E, then I just wanted to find the normal stress for our particular tube. You can't just use the normal stress from this graph because it doesn't apply to our solid tube. It just applies to something in general, right? So I cut my tube to get N. N was 40 kilonewtons. That's pretty simple. So sigma equals N over A, and I got 81.5 megapascals. The next step, once we found sigma and we found E, I found strain longitude, which is like along this axis right here. So I did 81.5 divided by 200, and that gave me some number here. And I also know that E longitude equals delta L over L initial. So that allows me to find delta L, so the change in length, once the stress is applied. And once I rearranged the equation, I just did this strain longitude from here times the initial length, which was 900 millimeters, and I got delta L equals 0.36675 millimeters. So we know the change in length at this point, and we know the initial length. Now from here on I moved to diameter. So they gave us Poisson's ratio, and we just found E longitude. So I used Poisson's ratio and E longitude to find E latitude, and that relates it to diameter. So once again I just rearranged my equation, plugged in the number I was given, the number I calculated, and I get latitude strain to be negative 1.4018 times 10 to the negative fourth. And you need to remember that these are unitless. Strains are always unitless because it's like a millimeter over a millimeter, so that's just 1, right? And then once I found E latitude, I know that E latitude equals delta D over D, so that way I can find delta D. So I did the initial diameter times E latitude that I just found, and I got my change in diameter to be negative 0.0035045. Okay, so now I've found my delta L, and I found my delta D, and I know that a change is just a final minus initial value. So I know both of my initial values, and I found my delta, and so I just did L final, and D final equals the change plus the initial value. So I get length final is equal to 900.36675 millimeters, and diameter final is equal to 24.9965 millimeters. And a really important thing to realize is to check if you understand the concept. So because this 40 kilonewton force is pulling the solid tube apart, that means that the solid tube is in tension, right? And when something is in tension, it becomes longer and it becomes thinner. So that's exactly what we got here. Our length was originally 900, but our final length was a little bit longer. and our diameter originally was 25 and it became slightly smaller. So that's a really good check right there.